In this video, I want to introduce an important tensor in the theory of elasticity. In particular, we will be talking about the strain tensor. We consider a certain body which can be deformed, so it's not a rigid body, and we describe a generic point of this body by using the coordinates xi. So xi is the certain position of this point with respect to a certain origin. So it's as if we consider a displacement vector. So it's a position vector labeled by the coordinates xi. Then a certain deformation occurs in a small amount of time, let's say, and then this point will get displaced to another point, which is xi prime. And the amount, so the deformation from xi to xi prime is given by ui. So this means we're using an equation that xi prime is equal to xi plus ui, or if you want, the definition for ui is given by xi prime minus xi. So ui is the amount of the deformation. It's a displacement. And now at this point, if we consider the distance between 2 points, two neighboring points of this body before the deformation, so let's say that we have these 2 points and we label this distance here, the displacement, the distance in terms of a vector is given by dxi, so it's a displacement vector, but the deformation has not occurred yet, so it's basically the distance between these 2 points before the deformation, and after the deformation, let me do it here, the distance between these 2 points will be dxi prime, and the dxi prime will be given by dxi plus dui. And now if we want to talk about the length, so the length, for example, of dxi can be written as dl squared, so the distance squared is given by dxi, and we have to sum over I, so we can also write it as dxi delta ij dxj, like this, with the Kronecker delta. And after the deformation, we have dl prime squared, and this can be written as dxi prime, like this. And we have the definition for dxi prime, so we can substitute it there. So basically, when I do the substitution, I get dl squared when we multiply dxi by dxi, and then we also get some cross terms. So we get plus, we have 2 dxi dui, or like this, so I can either write it like this or dxi dui with the different roles of these two indices, but what this means is basically that dxi, and then I have delta ij duj, so it can be written like that. And of course we also have dui dui like this, or if you want dui delta ij duj, like that. So now at this point I want to rewrite these quantities. In particular, this dui will depend on the xi's, so dui or duj in this case can be written as duj dxk, like this. And similarly I can do it in here as well, so I want to rewrite it as dl prime squared equal to dl squared plus 2, then I have dxi dxk, And then I can contract this delta with this duj here, so I can write dui dxk like this. Plus, then I can also rewrite this term here, so I can contract this delta ij with this duj. So I have dui dui, but I can rewrite these differentials in terms of the partial derivatives. So I have dui dxk dui dxj dxk dxj. And at this point, I want to use the fact that these are really dummy indices. I want to change this I to j, and I want to use the symmetry of these terms. So this term here with the 2 in front can be written as dxj dxk times duj dxk plus duk dxj. So I have simply used the symmetry property of this term. It's symmetric with respect to j and k. It's easy to see because we have the same differentials here with two different indices, which are dummy indices. And now I can put these terms together like this. So this is equal to dl squared plus, and then I'm writing 2 times 1/2 duj dxk plus duk dxj plus, and then I have dui dxk dui dxj, and then I have dxk dxj like this. And this object included in these square brackets is denoted by ujk, which is none other than the strain tensor. You can see that the strain tensor, this object, is symmetric with respect to the exchange of these two indices j and k. So ujk is equal to ukj. And if the displacements here are really small, we can say that this term here is quadratic in u, whereas these two are linear. So in case of small displacements, this term here, this object, can be neglected if ui is quote-unquote small. And anyway, you can see that since dl squared can be written as dxk delta kj or jk dxj, this can also be written in the following fashion: dxk dxj, then you have delta jk plus 2ujk like this. Now, this object here, ujk, since it is symmetric, it can be made diagonal. And if you want also this overall tensor here, given by the sum between these two, that's still symmetric because the Kronecker delta is symmetric, and therefore this tensor here is also diagonalizable. It can be made diagonal, and this means that basically, if we consider the three axes x, y, z, or x1, x2, x3, and if we assume that ujk can be made diagonal like this, so we have u1, u2, u3, and then we have all zeros in here, we can write the following. So the quantity square root of 1 plus 2 ui, so I'm using I here, and I can be either 1, 2, or 3, minus 1. This is basically equal to the relative extension given by dxi prime minus dxi divided by dxi along the principal axis. Let's give an example, a simple example. If we consider dl prime squared, this might be written as dx 1 prime squared plus dx2 prime squared plus dx3 prime squared. And this is also given by this expression, and we can make ujk diagonal along the three principal axes, and we can write dx1 squared, which multiplies 1 plus 2u1 plus dx2 squared, which multiplies 1 plus 2u2. And you also have the same for dx3 squared, 1 plus 2u3. So since the three directions 1, 2, 3 or x, y, z are orthogonal, they are also independent. And for example, the dilation that you have along the x1 axis is given by dx1 prime equal to the square root of 1 plus 2 u1 dx1. And similarly for the other two directions. So here we can write dx1 prime minus dx1 divided by dx1 as square root of 1 plus 2 u1 minus 1, and so on for the others.